In this video, we'll talk about decision errors. When we talked about visualizing data and we talked about the idea of outliers, we talked about the idea of outliers being scores with a very extreme value, either very high or very low. When we think about outliers, we also talked about the idea that oftentimes we will remove outliers from our data prior to analysis. And one of the reasons why we do this is because outliers might be different from the rest of our data. There might be reasons to believe that this outlier has a different score for a particular reason. And that's kind of what we're thinking about in a way when we're thinking about hypothesis testing. These particular scores that we're talking about aren't outliers, but when we're thinking about this kind of idea of hypothesis testing and when we're deciding whether or not we should reject the null hypothesis, what we're doing is we're comparing our sample score to the rest of our scores. We're comparing it specifically to our cutoff score, but our cutoff score is just a threshold of whether our sample score is different enough that we're going to say this score might not be from this distribution. Remember that we're comparing our sample score to our comparison distribution, to the distribution as though our null hypothesis is correct, and that there's no difference between our sample score and our other scores. Our effect essentially didn't work. Whatever medication or therapy or study strategy or whatever we're testing, there's no difference that's based on that particular manipulation. It's as though we kind of smushed all of these scores in this distribution into a bag and mixed them up. And if I pick out a random score, the idea is that generally I'm going to be picking a score that's closer to the mean. But if I pick out a really extreme score, like this 2.8 here, it's possible that that score actually isn't from this distribution. It's possible that I get this 2.8. We can see that that 2.8 is, but it's going to be much more rare that I pick this out by chance. And so if we've included some sort of manipulation, have some sort of an experiment where we're testing a medication or something else, the likelihood is that this score is a result of that manipulation, not just random chance. This isn't a score that we would just pick out at random from this distribution. But that means that our decision errors are the decision that we make, the conclusion that we come to, is based on probability. Our hypothesis testing procedure is based on probability. And so it's possible for us to make an error, and these are what we call decision errors. These errors are incorrect conclusions in hypothesis testing compared to the real but unknown state of the world. And so it's important to realize that when we make a decision error, we're not going to know that we're making it, but we have to have this awareness of the possibility to make these kinds of errors as we're going through our hypothesis testing procedure. And we'll see that this impacts, for instance, what kind of statistical significance level that we use. There are two types of errors that we can make. The first type of error that we can make is that we can reject the null hypothesis when we shouldn't reject it. And we can fail to reject the null hypothesis when we should. When we talk about the situation where we reject the null hypothesis when we shouldn't reject it, we call this a type 1 error. And we say essentially that an effect exists when in reality there's no effect. This is like saying that we've tested this medication and we conclude that it works when in fact it really doesn't relieve people's symptoms. But we have to remember that this is based on our statistics, this is based on the study that we've conducted, and we've made this analysis. It's not that we've made an error in our conclusion based on our data. Our conclusion is correct based on our data. It's just that the sample that we have randomly picked out of the world happens to not reflect what's going on with the rest of the people in our population potentially. This is an error that we really can't help, but we can try to prevent based on our significance level. Because the chance of making a type 1 error is the same as our significance level, and we have control over what significance level that we set. This is called our alpha. For our type 1 and type 2 errors, because we have a type 2 error also, we can try to make it so that our alpha is really, really low. It's going to be really, really rare for a type 1 error to occur. But the less likely a type 1 error is going to occur, the more likely that we're going to make a type 2 error. And so we have to balance these. And so we can't just make it so that let's try really hard not to make a type 1 error, because then we're actually inflating our risk of making the other type of error. And the type 2 error is when we fail to reject the null hypothesis when we actually should reject it. This means that we determine that our manipulation did not have an effect when it actually did, or when one really does exist in the real world. So for instance, we've tested this medication and we're determining based on the data from our sample that this did not relieve people's symptoms, this treatment did not work, when in reality, this medication is very effective and could potentially save lives. And so we can see the importance of these different types of errors, because we obviously don't want to be in a situation where we're giving people a medication that doesn't work, or we're not using medication and we're kind of throwing out this idea, concluding that this medication doesn't work, when actually we could be helping people. Because of this relationship between our type 1 and type 2 errors, as we said, we have to balance this. And this is actually part of why we use these kinds of standard significance levels, like less than 0.05 or p equals less than 0.05. This is a standard significance level that's widely accepted in the field. And the reason is because this is kind of a balance. We're going to kind of accept the risk that there is a 5% chance that our results are just due to chance or some kind of random effect, but we're still balancing and we're not making it overly likely that we're going to wind up with a type 2 error.